Well, welcome back. This is a very short podcast about solids. I find this to be a less than scintillating topic, so I'm going to keep it short. Solids have density because the strong intermolecular forces that keep them together make them densely packed. And many solids are crystalline solids who could have atoms or ions or even molecules arranged in a very orderly three-dimensional geometric structure. So in an ionic solid, for example, we learned about unit cells that repeat over and over again to form a crystal lattice framework. Here's an example of a unit cell, kind of a tilted cube or a rhomboid shape. And down at the ionic or the atomic level, the ions or atoms will join together in a tilted rhomboid shaped crystal, but then as they grow and grow and grow, even when they get to the large scale where we can see it with our eye, they will still have the same shape that was originally determined by the ions or atoms down at the unit cell level. There are lots of different shapes of crystals. Here are just three of the many. These are cubic crystals. Primitive simply means that it forms a cube, and that's it. But a body-centered cubic crystal has an atom or ion here in the center. And a face-centered cubic crystal still has the cubic shape, but you can see that on each face of the cube they've embedded an atom or an ion. These are what we call space-filling models of the same shapes that you see over on the left, and gives you a better idea of how those ions or atoms would be interacting with each other. But overall, highly organized and crammed in close to each other, dense. Here is a picture of sodium chloride. Here is a repeating crystalline shape of a cube. Salt crystals are little cubes. And again, here's the space-filling model showing that the positive, smaller purple sodiums are attracted to the larger green negative chlorides because opposite charges attract. Many shapes of crystals. You do not need to know these, but keep that in mind next time you go to a natural history museum and you look at the gemstones that are in there. The beautiful shapes they have are determined by the arrangement down at the atomic or ionic level. Now there are four basic types of crystalline solids. Let's look at three that we already know about. Let's pick one that's pretty easy. Ionic substance. They're made of positive and negative ions because they're oppositely attracted to each other. And we learned that ionic substances are hard and brittle, typically have a high melting point, and unless you dissolve or melt them, you won't have conduction of electricity. We took a whole chapter and we studied molecular substances. Actually, they're made up of atoms or molecules, and the forces that are between the particles are the three that we have been studying in this chapter: dispersion forces, dipole-dipole, and hydrogen bonding. They have a wide range of melting points, and thermal and electrical conductivity is generally pretty poor, and they consist of either elements like argon, or molecules like methane, or big molecules like sugar. Finally, we studied metallic substances, which are made of atoms bonded to each other through metallic bonds, and metals can have a wide range from being very soft to very hard. Mercury is a liquid at room temperature, but tungsten is the hardest metal known. They can go from very low to very high melting points, but metals are good conductors of electricity because their structure allows electrons to flow. So it leaves us with this weird one called covalent network. They consist of atoms that are connected together in networks. So they're not standalone free atoms moving around. They're all attached to each other with covalent bonds. That makes them very hard with high melting points. And a perfect example of that would be diamond. Let's take a close look at the difference between diamond and the lead, which is not lead, the graphite that's in your pencil if you're writing with a pencil right now. They're both made of carbon atoms. They're allotropes of each other because they're both solid forms of the same element. And at first they look similar, but the diamond has these covalent bonds between different atoms that link three-dimensionally all throughout that crystal of diamond. So that's what makes it very hard. Interestingly enough, the atoms always look black in these pictures, but in fact a diamond is beautifully clear and transparent. Graphite are hexagonal rings of carbon that attach to each other through these covalent bonds, but then they form layers, And those layers have weaker forces of attraction between them that allow, when you press on a pencil, for the layers to rub past each other, leaving the pencil mark on the paper. But both of these are covalent network solids. Here's another example of ionic substances. They're oppositely charged positive and negative ions, sometimes polyatomic, arranged in highly ordered crystalline lattice. Here's that picture of the metallic bond. We think of the centers of the atoms of metal staying put. That's what the big plus signs stand for. But the blue color represents the sea of electrons that wash all around that crystalline structure of the metals, allowing them to hold together because the positive centers are attracted to the negative electrons all around them, but allow them to be also malleable and ductile. You can push on a metal and stretch it into a thin wire or pound it out thin and flat because it's strong enough forces to hold the metal together, but weak enough to allow for malleability and ductility. The one that we've never spoken of is called an amorphous solid. And when you look at an amorphous solid with superhuman vision, you see a pattern that is not regular and repeating. A means without, and morph means shape. So amorphous means without a specific shape and includes things like glass, plastic, and rubber. Here's a close-up of an amorphous solid on the right-hand side. Both of these substances are silicon dioxide. When you've arranged yourself into a highly ordered quartz crystal, you're going to have a regular pattern that repeats. The forces of attractions are quite strong, and that's crystalline silicon dioxide. But when you take glass and look at it carefully, you'll find that, yeah, every now and then I see some highly ordered attachments of atoms to each other, but the red oxygens and the blue silicons and the rest of this amorphous solid don't have a regularly repeating pattern. The forces of attraction here might be quite weak, whereas in this part of the sample, quite strong. So one of the characteristics of an amorphous solid is that it melts at different temperatures. The part up here with weak attachments might start melting at a much lower temperature than this portion down here. When you look at old glass, which this is supposed to represent, you may often see ripples in the glass. And that's because some people think of the glass as being almost like a liquid. It sags over time. And that's because these forces of attachment to each other are weaker, and literally the old glass is sagging within its window frame. That's the end of the shortest vodcast in this chapter. I am quite relieved. Take care.